Hello everyone and welcome back to physics class. Today we are going to continue the topic of resultant forces, but we're going to talk about a very special case. And this is the case where the resultant force, which is the sum of all forces acting on a body, is equal to zero. This is called equilibrium. Now, a body in equilibrium cannot be in acceleration, so it cannot be speeding up and it cannot be slowing down. However, this body that is in equilibrium can be in a moving state. So it can be in a static or non-moving state, but it can also be moving, provided that it is moving at a constant velocity. So we actually have two categories for equilibrium. We have static equilibrium, which is when we have an object that is not moving. And then we have dynamic equilibrium. And then this is when something is moving at a constant velocity. So when we go and look at the generic formula for this, we're basically saying that when we add up all the forces, so like F1 plus F2 plus F3 plus so on and so on, it all equals up to 0. Now, we have to make sure that this is along each axis. So that means that this is actually F1x, F2x, F3x that is equal to 0. And then we also have F1y plus F2y plus F3y plus ... is equal to 0. So when we are looking at equilibrium, we want to make sure that it's 0 in both the x and y axis. So let's go ahead and take a look at an example. So in this case, we have a mother is pushing a baby carriage with a horizontal force of 600 newtons. The friction force felt by the carriage is 400 newtons. Is the carriage in a state of equilibrium? So let's draw our free body diagram of the carriage. So we draw a dot to represent the carriage, and let's draw all the forces acting on this carriage. So we know that there is the gravitational force that pulls down, and we're assuming that this is on some kind of surface like a road or a sidewalk, and so there is the normal force that is pushing up. Now, there's also the applied force, and I'm just going to say that the applied force is pushing to the right. And we actually have a value for this. We know that this is 600 newtons. And finally, we have the friction force, which goes in the opposite direction of our movement. So if it's moving to the right, friction is going to the left. And it is kinetic friction because it's moving, and that is 400 newtons. So let's go ahead and evaluate, is this carriage in a state of equilibrium? Notice how we weren't given any information about the gravitational or the normal forces. This is because it is assumed that we are walking on a flat surface and that there's no movement happening in the vertical. Since there's no movement happening in the vertical, then we know that it is in static equilibrium in the y-axis. Now, when it comes to the x-axis, we have two opposing forces here, and they both have values. This one's 600 and this one's 400. So you can probably see right away that these two forces don't cancel each other out. If we were to add up all of the forces in the x-axis, so Fx, it would be equal to positive 600, remember this is the positive direction, minus 400, which gives us 200 newtons. This is not equal to 0, so therefore, the carriage is not in equilibrium. And that's really all there is to it. You just need to make sure that it equals up to 0. If it doesn't equal to 0 in any of the x or y axes, then it is no longer in equilibrium. Thank you for listening, and I will see you all next time when we talk about equilibrium on inclined planes, not flat surfaces. Till then, bye!